Okay, so today, so far, we have actually just revisited the examples that were described in the last class. Now it's time to give a new example. Actually, we'll give two new examples, but we'll start with one. This is called gambler's ruin problem. So you fix two positive integers, a and b. Suppose you have two gamblers, A and B, capital A and capital B, which have in their pockets rupees A and rupees small a and rupees small b, respectively. And that's all they have. No other money they have. Now they decide to play the following gambling game. What is the game? They keep on tossing a fair coin independently. Each time a head appears, A gives rupee 1 to B. On the other hand, whenever tail appears, B gives rupee 1 to A. Now this process goes on till one of them is finished with the money. Okay. The question is, what is the probability that A is ruined? In other words, A runs out of money. So this is the same question as asking, what is the probability that B will win the game? This is a game. So it will be one provided the other person is ruined. So now this is a famous gambler's ruin problem. And to be honest, the coin does not have to be fair. It's just I'm giving the simplest possible example. That's why I'm keeping the coin to be fair. Now, what is this anyway? So let's try to formalize this in mathematical terms. Suppose XM is the amount of money in rupees that gambler A has after M tosses. So whenever I say M tosses, I mean after M tosses, and after that toss, immediately either the gambler will get some money or the gambler has to give the money. After that, how much money does the gambler have in his or her pocket? Now then, it's not hard to check that XM is actually a Markov chain. And what is the state space? The state space is that all integers from 0 all the way up to A plus B. Why is it so? Because, of course, the gambler each time is giving 1 rupee and started with an integer amount of money, rupees A namely. So therefore, always he'll have an integer amount of money. So it's obvious that this XM can only take values integers. Now it cannot take anything below 0 because the moment it reaches 0, the gambler is ruined and the game is stopped. So therefore, the gambler will remain at 0 from then on. On the other hand, if the gambler reaches A plus B, gambler A reaches A plus B, that means B is ruined because B has given away all the money to A and B is ruined, and then the game has to stop. So therefore, this is the all possible values that XM can take. Now, what is the initial distribution? The initial distribution is the gambler A is starting with rupees A. So therefore, the initial distribution is delta A. X0 is A with probability 1. And the transition probability matrix Pij is given as follows. So if I is taking any of the values except the boundary values 0 and A plus B, then it will go to one of the nearest neighbors with equal probability. So from I will either go to I plus 1 or I minus 1 with probability half. On the other hand, if you in one of the terminal values, like if one of the values at either at 0 or at A plus B, then you've already reached the final value because either you are ruined or your opponent is ruined. In either case, this Markov chain is not going to move at all. So in other words, if I is either 0 or A plus B, then PII would be 1. That's precisely given. So the Markov chain will just stay put at that particular value. the game will stop essentially. And of course, there no other transition is possible. Now, while this description is nice and mathematically looks beautiful, in terms of presentation, this is not the best way to do it. And physicists actually use something called a transition diagram. And we already used it, but now I'm going to show you, in this case, how useful it is. The transition diagram is this. So you start at, say A is 3 and B is 2. I'm just giving the transition diagram in that case. So of course, the Markov chain will be, the state space would be 0 to 5. 0 to A plus B, so A is 3 and B is 2. So the 0, 1, 2, 3, 4, 5, that's the state space. Now in any of these values, 1, 2, 3, 4. So by the way, you start at 3 because A is 3. So this is the Markov chain that gives you the amount of money A has after M tosses. Similarly, you could have done it for B also, but I just chose A. Anyway, since small a is 3, the Markov chain starts at 3. Now, if you're at any of these values, 1, 2, 3, or 4, any of these interior values essentially, not the boundary values, not the terminal values, then you either go to your neighbor on the left side or go to the neighbor on the right side with probability half and half respectively. See, for all of them, this is true. 1, 2, 3, and 4. On the other hand, if you're at 0 or you are at 5, then one of the gambler has ruined. Okay? One of the gambler is ruined. So in this case, gambler A is ruined. So of course, the transition will only happen from 0 to 0 with probability 1. On the other hand, if XM has reached 5, then gambler B is ruined, and then therefore the transition will always happen from 5 to 5 with probability 1. So this is the transition diagram. Okay? So therefore, we'll need a little bit more notations here. By the way, this has another name. So before I write those things, those notations, I need to tell you that this has another name. If you forget about what happens at 0 and what happens at 5, you're essentially seeing a simple random walk on integers, right? I mean, wherever you are from 1, 2, 3, 4, you're always moving to one of the nearest neighbors with equal probability. But that's exactly what happens in simple random walk, except that you started at 3. In simple random walk, the way I presented it, we started at 0, but there was no hard and fast rule that you have to start at 0. In this case, we decided to start at 3, and then we are doing simple random walk, except that the moment we hit 0 or 5, we get absorbed at that point. We don't move at all. We stay there with probability 1 once we reach there. Okay? So this 0 and 5 would be called absorbing states for this Markov chain. Once the Markov chain goes there, it stays put. It doesn't move from there. Okay? This has another name. It's called a simple random walk starting from A. And of course, it's on Z. I'm not mentioning it. So if you don't mention anything, simple random walk just means simple random walk on Z. Starting from A with absorbing barriers 0 and A plus B. See, in other words, it's the same transition probability. It's the same thing. We are just performing simple random walk, except that the moment we hit either 0 or A plus B, we get absorbed and we stay put. That's why it's called simple random walk with absorbing barriers 0 and A plus B. And of course, it starts from A. So fix A and B positive integers and let XM be a simple random walk starting from A with absorbing barriers 0 and A plus B. So this is basically just the gambler's ruin Markov chain, nothing else, with the same transition matrix as we have given. Transition diagram also is given. Now, here is an exercise for you. show that with probability 1, the Markov chain gets absorbed either at 0 or at a plus b. Now this does need some work in the sense that starting from 3, you may just go on going, oscillating between 1 and 4 throughout your life and never reach 0 or 5. This can happen. But what it is saying is that this will happen with probability 0. So you cannot just stay between 1 and 4 forever. So show that with probability 1, the Markov chain actually gets absorbed either at the left endpoint or at the right endpoint of this picture. Now, more precisely, what I'm asking is this. Define a random variable tau to be first time the Markov chain gets absorbed. In the sense that first time the Markov chain hits either 0 or a plus b. Okay? It's the infimum of all m bigger than or equal to 1 such that xm is either 0 or a plus b. Now obviously tau is at least 1 because you know that x0 is a, which is strictly bigger than 0 and strictly less than a plus b. Now in this case, x0 is 3, and then you're looking at first time the Markov chain either hits 0 or hits 5. Okay? So this is the tau, and then what I'm asking you to show is that the tau is finite with probability 1. So tau infinite would mean that this set is unbounded, so which means that xm never reaches 0 or a plus b. So it always remains in the interior values. But that happens with probability 0. So that's what I'm asking you to prove. So show that this random variable tau that we define, this is an integer valued random variable, of course. This random variable tau is finite with probability 1. And this has nothing to do with Markov chain theory. It's just an exercise that can be done from your knowledge of probability theory 1, actually. Okay? And the hint that I'm going to give you is that bound this random variable tau by a random variable, another random variable that's finite with probability 1. Think of a random variable that will be bigger than this tau, okay, and that will be an upper bound for this tau, and that random variable is finite with probability 1. That random variable is obviously finite with probability 1. Okay, so this is the hint. Okay, so suppose xm is a simple random walk starting from A with absorbing various 0 and a plus b. So this is the transition diagram. And then if you accept that exercise as a fact, then the random variable tau, which gives the time of the Markov chain to get absorbed for the first time, okay, that random variable tau is finite with probability 1. Now note that x tau is the final value of the Markov chain. So x tau gives where the Markov chain gets absorbed. Obviously, tau is finite with probability 1. So therefore, the Markov chain does get absorbed somewhere. And x tau, which is essentially x1 when tau is 1, x2 when tau is 2, x3 when tau is 3, and so on. Okay? So this is basically gives you where exactly the random variable, the Markov chain get absorbed, whether it get absorbed at 0 or it gets absorbed at a plus b.